Okay, so hello. We can view the last time's discussion of a particle which is being applied a certain force or it is in a field and it is going in some trajectory by a different type of scenario or rather analysis. We can do a different analysis on that, and that is what the action principle is. Okay, so what we're going to do is we'll define what the action principle is, and then from that principle we are going to derive the Euler Lagrange equation. So let's say again we made a particle from, let's say it goes from point A to point B. Now imagine that we know that where the particle is at point A and where the particle is at point B. So we know the initial and final points, but we don't know the trajectory of the particle. So let's say the particle might be going in this particular trajectory if I apply a force, or it might take a completely different trajectory of this dotted line, or it might take any type of this certain type of trajectory. So it can take infinite paths. So there can exist infinite paths in principle in which this particle might have gone, but in reality we see that it only follows a solid line path. So why is it so? That is the question we ask. Like, is there any particular quantity which is defining this particular path for the particle apart from solving the Euler Lagrange equation or solving the equation of motion? So it turns out after several years of analysis that indeed there is a particular quantity which is being stationary, and I will tell you what the stationary means when it follows this solid line trajectory. So that particular quantity is action. So it is a principle of stationary action. Historically, it was being called the principle of least action, but now we know that it is a principle of stationary action. Not necessarily every time the stationary action leads to the least action. And sometimes it does, but not every time. So we'll just call the principle of stationary action. Okay, so what does the principle of stationary action exactly means? So imagine in a very abstract manner, imagine a quantity A, call it action, and now you view trajectories. So let's say I'm again making point A and point B, and let's say this is the real trajectory of the particle. Okay. Now what you can do, you can imagine a slightly different trajectory, a slightly deviation from this original trajectory, something like this. Let's say something like this. So this dotted line trajectory is a very little deviation from the original trajectory. So this little deviation we can call, like, at every point it is deviating with epsilon. It is deviating with epsilon here, where epsilon tends to 0. And then for different epsilons which tends to 0, you can get different of these very close trajectory. So the principle of stationary actions tells you that for all of these very small deviations of trajectory, so let's say I have a T1 trajectory 1, trajectory 2, trajectory 3 for epsilon 1, epsilon 2 and epsilon 3, they all have the same action for the overall trajectory. So when this happens, we say that our action is stationary for the little deviation. Okay, now I'm going to define what is this quantity action in terms of the Lagrangian, which we have seen in the previous video. So the action is equal to Lagrangian integrated over time from k to p. So this is the action. This is that abstract quantity which we are wondering, and this quantity turns out after, and you can even check by yourself for some cases that when you integrate this quantity for the original trajectory, for the real trajectory, you will get that yes, this quantity is stationary, or rather in some cases you will find that this quantity is minimum or this quantity is maximum for their original trajectory in which the particle goes and which you also observe, okay, or which you solve from the equation of motion. So if the if the principle of stationary action is true, then we should be able to derive the Euler Lagrange equation from this particular action here. So that is the purpose of this video. Okay. So now what we can do is we can imagine delta A. Delta A is what? Delta A is variation in action. Let's say my action varies. Okay. Why the action will vary? Because let's say there is a variation in Lagrangian. So this is variation in Lagrangian. Okay. So A to B, from A to B, this variation is for these different dotted trajectory. So every different trajectory, T1, T2 or T3 trajectories, my Lagrangian will vary because the coordinates are not same anymore for different trajectories. Hence, there will be a variation. So we can write from here the variation in action due to a variation in Lagrangian would be delta LDT. And we know that from here that the variation in coordinates, the variation in coordinates at A and B. What will be the variation in coordinate at point A and at point B? So we see that the variation, let's say the coordinates are represented by delta Q or delta X, let's say. So delta X at A is equal to delta X at B is equal to 0. Why? Because in the starting of this discussion, I told you that trajectories points, end points are fixed. So that's why no variation at the end points. It follows from that. Okay. So now what we are interested in? We are interested in solving the RHS, the variation in delta L, as a function of the coordinates or as a function of coordinates and velocities. Okay. So let's say I have Lagrangian L, let's say I have Q, okay, Q dot and T, where Q dot is basically dq over dt, right? So it's the Lagrangian. Now delta L can be written as del L over del Q, delta Q, Q is coordinate, okay, plus del L over del Q dot and delta Q dot. Fine. T is the variable for integration here. So anyways, when we say that the trajectory is varying, we are watching I mean, we are anyways integrating over T. So the variation of Lagrangian, the T is not varying. T is not a varying variable here. It is being integrated over. That's why no T here. So what we can do from here is we can write delta L del L over del Q delta Q plus del L over del Q dot and d by dt of del Q. This is something we can do. Now what we can do, we can imagine that this d by dt, we can see the ultimate aim is to find the complete derivatives. Okay, because we know when we find complete derivatives, we can directly integrate over. So that's what we have to do with the second term. So what we can do is we can write del L over del Q dot d by dt of del Q is equal to complete derivative of the both quantity combined like this, and we have to subtract d by dt of del L over del Q dot with delta Q. Okay, seems correct to me. Now what we can do, we can just simply substitute this quantity in delta L. So the variation in Lagrangian will be del L over del Q delta Q plus d by dt del L over del Q dot delta Q and minus d by dt del L over del Q dot delta Q. We can obviously club the first and third term and find the delta Q common. So it will be del L over del Q minus d by dt del L over del Q dot. And there is a complete derivative term which is quite clear here, del L over del Q dot delta Q. Now here comes the trick. When we integrate over now delta A from A to B was delta L dt. Okay, now this can be written as dt delta Q del L over del Q minus d by dt del L over del Q dot. This is my first term, and the second term when integrated, because this is a complete derivative, so it will just give you the boundary terms. Okay, because it is now being integrated over del L over del Q dot and delta Q, but from A to B. Now I have mentioned earlier that the delta XA, okay, here I've used delta XA, I can also write delta QA is equals to delta QB is equals to 0 for coordinates, because there is no variation at the boundary points, because the boundary points are fixed in our analysis. So we can simply write this terms, this term go to 0. Okay, now my delta A simply becomes dt from A to B delta Q and the term inside bracket. Okay, so now we see that for stationary action, for stationary action, we already saw that for stationary action, these tiny deviations of delta A should be 0. That is what the word stationary means. Basically, there is no deviation. So for little deviation in trajectories, in trajectories, there is no deviation in action. This is the term stationary means from the calculus. The stationary action means delta is equal to 0. So if the LHS has to be equal to 0, then RHS is also equal to 0, and we see that it is an integration over. So the only way the RHS is equal to 0 for all the choices of Lagrangian, for any crazy choice of Lagrangian, because it holds for all the cases. This tells us that the integrand itself is equal to 0, which is nothing but yields the Euler Lagrange equation, which we saw earlier. This is nothing but the Euler Lagrange equation. And we also saw that they are equivalent to Newton's laws as well. So at this point, we have concluded that our action principle actually works, at least for non-relativistic classical mechanics. At least for non-relativistic classical mechanics, the action principle completely works. Okay, and we have proven the Euler Lagrange equation, which I have also proved that they are equivalent to Newton's laws. Okay, so from here, the next point is to develop the relativistic classical mechanics, leaving behind the Newton's laws, because we know that Newton's laws, the second law, it works for relativistic. It was formulated in relativistic classical mechanics. Then, sorry, it was formulated in non-relativistic classical mechanics. The relativistic classical mechanics has these concepts of time dilation, and it treats the time as the fourth dimension. So what we have to do is we have to leave behind the Newton's laws, and then we have to start from the Lagrange. So for relativistic mechanics, challenge is to find a suitable action. If we are able to find a suitable action, we can develop the theory of relativistic mechanics. So see what the momentum is and see what the energy is, and then see the relation between them, and hence able to do a lot of physics there. Okay, so that would be the content of next video. Yeah, that is pretty much it for this video.